Swayam Prabha. Digital India. Educated India.
So, we will be looking at plug flow recycled reactors today. Okay. This is something that we have spoken about earlier. Recycle. See, here is an instance of a plug flow reactor in which this material is taken out and put back. Now, why do we do recycle? Now, of course, recycles are common in process industry because the reactions do not go to completion. So, you separate and recycle. So, the separation part is not taken into account yet, but the fundamentals of recycle is what we want to understand and set up the basic approach to looking at recycled reactors. Now, just to make it a little easier, what I have done here is I have taken position 0, 1, 2, 3 and 4 to indicate the different positions in the equipment. Okay. And I have taken two instances where there is no catalyst in the reactor and second instance where there is a catalyst in the reactor. Now, case 1, when there is no catalyst in the reactor, for example, if you take recycle ratio as 4, I have just put down what are the flows going through at different positions. Let us just go through it for instance. I have taken FA0 as 1 and therefore, FA3 should also be 1 because whatever comes in must go out. Okay. I have taken R as 4, therefore, FA4 is 4 times FA3, therefore, R is FA4 is 4. And there is no reaction, therefore, FA1 should be FA0 plus FA4 which is 5. Okay. So, FA0, FA1, FA2, FA3, FA4 this shows the number of units that flows through the equipment when there is no catalyst, that means there is no reaction. Now, let us say there is an extent of reaction of something like x equal to 0.4, which means out of 1 unit that is coming in at position 0, 0.4 reacts, therefore, the balance is 0.6. So, if balance is 0.6, therefore, at position 4 it should be 4 times 0.6, therefore, it is 2.4. If it is 0.6, 4 times 0.6 is 2.4. Now, at position 2 it should be FA4 plus FA4 plus FA3 is FA2, therefore, it is 2.4 plus 0.6 which is 3. Okay. And FA1 it should be FA0 plus FA4 which is 3.4. So, this tells us based on material balance what are the flows at different positions. Now, what we would like to see is since there is no reactor between position 2 and position 3, common sense tells us that the value of conversion that we calculate must be the same at 3 and 2. This is common sense. So, how do we make it the value of conversion to be the same? We recognize that conversions are defined on the basis of a reference. Every time we have a reference basis of which we define conversion. Therefore, here if we take our reference as what flows into the equipment in the absence of reaction, which is 5 units, then we notice that conversion at position 2 becomes x a equal to 0.4. 3 divided by 5 is 0.6, 1 minus 0.6 is 0.4. So, common sense tells us that the reference on which we should define conversion inside the loop must be the units the material that flows into the reactor in the absence of reaction, or putting in terms of recycle ratio, FA0 is when there is no recycle, there is R is 0, and when there is recycle then it should be R plus 1 Fs, correct. So, the basis for defining conversion inside the loop should be R plus 1 Fa0. If there is a different definition, then our formulations will change, but the important thing is that as you will see as you go along, our formulations do not change much. If you use this definition, you find that when you put R equal to 0, you get what we would have gotten when we did not have any recycle. So, that is the advantage of this formulation, but it does not matter as long as you are very clear about the definition, it does not matter. Okay. Okay, let us just take it as in the absence, if the within the recycle loop, we should have r plus 1 f a 0 as the basis. Okay. So that when we go outside the loop, r is 0, our basis becomes f a 0. So, it is consistency between inside and outside. Okay. In the absence of, which means what enters the reactor in the absence of reaction. Just to make it clear, I said in the absence of catalyst, there is no reaction. Therefore, what enters at 5 at 1 is 5 units. That is how I explained it. Okay. So, I have calculated what is the conversion at 1. Conversion at 1 should be 3.4 divided by 5. So, what is 3.4 divided by 5? 1 minus, is it okay? 0.32. So, it shows that conversion here is 0.32 and here it becomes 0.4. So, important thing to recognize in plug flow recycle is that per pass conversion going from 0.32 to 0.4, but overall conversion is 0.4. Overall conversion 0.4, per pass conversion is 0.32 to 0.4, only 0.08. So, per pass conversion is low, but overall conversion is high, and there are certain advantages for this. We will look at this as we go along. Is that okay? So, I am just summarizing what we have said already, that flow entering the reactor in the absence of reaction is r plus 1 f a 0. Okay. Therefore, the basis for defining conversion within the recycle should be r plus 1 f a 0. Therefore, value of x 1 is 0.32, x 2 is 0.4 and x 3 is 0.4. There is consistency between inside and outside the loop. So, we will go further now. Then I said we can calculate per pass conversion. In this particular case, for example, what is per pass conversion? F A 2, so it is reverse, F A 1 minus of F A 2, I should have, it is F A 1 minus of F A 2, this is per pass conversion. So, it is 3.4 minus of 3, this is how it will come out to be, okay, 0.117. Now that we have said that the basis for defining conversion is r plus 1 f a 0, we can write the stoichiometry. Just like we have written stoichiometry before, we can write stoichiometry again. That means, what comes into the process is r plus 1 f a 0, r plus 1 f 0, r plus 1 f c 0, r plus 1 f d 0, r plus 1 f I 0. Therefore, the total is r plus 1 f t 0. When r is 0, it is same as what we had before. Now, what goes out, since A is our reference, r plus 1 f a 0 times 1 minus of x a is the flow rate of component A at any position inside the loop. Inside the loop, it is at any position. Okay. Similarly, for component B, it is r plus 1 times the f b 0 is coming in, and this is the amount that is reacting. For component C, r plus 1 times the f 0 entering, and this is the amount that is reacting. Similarly, component D, similarly component I. So, that when you add up all this, the total moles of components at any position is r plus 1 f t 0 plus r plus 1 f a 0 delta s, or in other words, you find that f t by f t 0. Notice here, what is this f t 0? F t 0 is actually what is entering outside the loop. Okay. F t 0 is what is entering outside the loop. You can see the way I have formulated it. F t 0 is what is entering outside the loop. F t is what is inside the loop. And therefore, this term is exactly the term that we had earlier, only thing it is multiplied by r plus 1. So, when you put r equal to 0, it is exactly what we had before. The consistency is what is important. Outside the loop and inside the loop, the consistency, simply put r equal to 0, you get what you got before. F t is any position inside the inside the recycle loop. We are talking about inside the recycle loop. So, that when you put r equal to 0, you find you get the same result that we got before. At this point, in the absence of reaction, this is what is entering. What we are trying to say is that when we are trying to look at the recycle system, our basis should be r plus 1 times what enters the reactor in the absence of reaction. I think this is the fundamental difference that we must recognize towards recognizing the basis, because we need a basis to define conversion, and that is why we said this is the basis on which the reaction takes place. So, basis is r plus 1 f a 0. Therefore, all our conversions are assuming that r plus 1 f a 0 is going through the reactor. And how did we come to this r plus 1 f a 0? We took the example to understand this, that when there was no reaction, 5 units was entering, and therefore, our basis should be 5 units, and we also found out that only when we do that there is consistency between position 2 and position 3, same value of conversion. So, that consistency will not be there if you do not define it this way. So, the important thing is only the choice of the reference is important in recycle. Let us look at the example that we have. Let us go back to the same example and ask all these questions. Let us ask all these questions. When there was no catalyst, we said 5 units was going through at point 1. When there is a catalyst, we find that at point 2 it is 3. So, the conversion at point 3 is 0.4, conversion at point 3 is 0.5. Therefore, between 2 and 3 you see consistency. This consistency is fundamentally required for us to choose the reference. The reference is to be chosen to get this consistency between 2 and 3, and that we have got by recognizing that 5 units was flowing at point 1 when there was no reaction, and FA0 is what? In the absence of reaction, correct. The meaning of FA0 is what enters the process, that means when there is no reaction at that point, correct. So, in the same way, what enters at position 1 in the absence of reaction is 5 units, and in our nomenclature it is R plus 1 FA0. Is that clear? Answer to your question is, we said between point 2 and point 3 we need consistency. That means, the value of conversion at 3 and 4 should be 2 and 3 should be the same, because only then as you move from 2 to 3 the value of conversion does not change. That is the consistency we require in our definition or in our choice of reference, and we said that reference choice is R plus 1 FA0. Only then we get this consistency. Is that clear? So, consistency comes only when we choose our reference properly, and reference is what enters the equipment in the absence of reaction, and that makes sense also. What enters the equipment in the absence of reaction should be our basis anyway, correct. See, if so much of sulfur dioxide is entering, that is the basis, so that we can find out how much of sulfur trioxide is coming, correct. So, in the same way, between point 2 and point 3 we must have consistency in the value of x. That is why 5 units is chosen as the reference. That is why R plus 1 FA0 is chosen as reference. When you put R equal to 0, it becomes our conventional definition that we have been using all the time. So, having said this, let us go further now. So, what are we saying now? The total moles that is coming out of our, let me draw the recycle once again. This is our recycle system. Okay. So, total moles at any position. So, F t is at this point F t, okay, is R plus 1 multiplied by 1 plus y a 0. This is the position 0, y a 0 refers to this position. This is 1, this is 2, this is 3, this is 4. Okay. So, this y a 0 refers to position 0. Okay. Delta A refers to our stoichiometry. X A is conversion at this point, which is consistent with between 3 and 2. Okay. Now, what we are now saying is that if you want what is the conversion at position 1, if people ask, our answer is at position 1 as per our definition it must be R plus 1 F A 0 1 minus of x 1, that is our definition. Our material balance tells us it must be F A 0 plus F A 4. Okay. What is F A 4? It is R times F A 0 times 1 minus, correct, because we are recycling R times 3. So, F A 0 plus R times F A 0 1 minus, this is F A 3, we know that this is F A 3, correct. So, this is the statement of material balance. Therefore, it gives you this relationship that x 1 is R by R plus 1 x 3. So, what does it mean? It means that per pass conversion is quite low, while overall conversions can be quite high, depending on the choice of R. Depending on the choice of R, if R is very large, what does it mean? X 1 becomes very close to x 3, which means what? The per pass conversion in the equipment is very low. So, you have very little conversion here between point 1 and point 2, per pass is low, okay, but the overall can be quite high. Okay. Let us go forward. So, what is per pass conversion? If I say our position 2, this is our position 2, okay, 0, 1, 2, 3 and 4. So, what is per pass conversion at 2? Y F A 1 minus F A 2 divided by F A 1. So, it comes in terms of x 2. So, when R is large, you can see that per pass conversion is quite low. So, if you ask yourself when would you be interested in a low per pass conversion? When you do not want a very high temperature rise. So, or in other words, if you want to operate an equipment isothermally, because you want to do chemical kinetic measurements, that means you want isothermal data. You can get isothermal data in this kind of environment. So, if you have a catalyst which you have prepared, you want to evaluate that catalyst and determine the chemical kinetics of that catalyst, you can do measurements at isothermal conditions in a recycle kind of device. And it is relatively easy, because it is the catalyst does not get spoiled, because it is not moving and so on. There is a lot of advantages. Okay. All right. So, let us look at the design equations. So, what is our design equation now? You have to take a material balance in a volume delta V, okay, where the flow rate at that point is R plus 1 F A 0 1 minus of x A. This is our stoichiometric table, this is how we have defined, and our material balance tells you that dF dV equal to R A. This is something that we have done, this is for a PFR. The only thing that has changed now is that our flow at this point is R plus 1 F A 0 times 1 minus of x A, correct. This equation dF dV equal to R, there is no change, but value of F A at that point is R plus 1 F A 0 1 minus of x A, because our basis for defining conversion is R plus 1 F A 0. Therefore, the design equation for a recycled reactor becomes what is mentioned here, V equal to R plus 1 F A 0 integral x 1 to x 2. We are going from 1 to 2. So, let us look at this at some detail. So, our design equation is R plus 1 F A 0 going from 1 to 2, where value of x 1 is R by R plus 1 x 2 and x 2 equal to x 3 as per our definition. Now, let us ask what happens to this when value of R is large. What is the value of this integral? What I have done, limit as R tends to infinity, I have just tried to find the value of this integral. When R is very large, I have just said dx A is simply x 3 minus R x 3 by R plus 1. So, this integral, and I evaluated the denominator minus of R A at the mean value of x. What is the mean we have to take? Between x 1 plus x 2 divided by 2, correct. So, this x mean refers to x 1 plus x 2 divided by 2 when R tends to infinity. Let me repeat, we are trying to find out what happens to this when R is large. This design equation, what happens when R is large. So, I am taking limit R tends to infinity of R plus 1 multiplied by this integral. This integral I have written as dx A, I have written as x 3 minus R x 3 by R plus 1. Denominator I have written as R x at x mean, which is x mean means x 1 plus x 2 divided by 2. Is this clear what we are saying? So, let us look at this. So, x mean, I have just calculated the value of x mean. You can say here the limit as R tends to infinity of this, it goes to x 3. You can do it yourself, it is fairly elementary. So, the limit of this as x tends to infinity is x 3. So, that this whole integral now becomes x 3 divided by value of R A at x 3. Is that clear? What we are saying is this mean is at x 3, and you can see here this whole thing becomes x 3 only. So, numerator becomes x 3, R plus 1 gets cancelled. Therefore, and this whole thing becomes value of R A at the mean value, which is x 3. Is that clear what we are saying? This limit as R tends to infinity, this whole thing becomes the numerator becomes x 3 and the denominator becomes value of R A at x 3, because the mean at R tends to infinity becomes x 3. So, what are we saying? What we are saying is that when R tends to infinity, this whole integral, the whole thing actually becomes, the equation becomes same as a stirred tank. This integral here, when R tends to infinity, by going through this procedure we have shown that it becomes, the equation becomes same as a stirred tank. When R is large, the recycled reactor equation becomes that of a stirred tank. So, what it means is that stirred tank is an instance of a plug flow recycled reactor with infinite recycle. Okay. With infinite recycle, that is when it becomes plug flow. Is that clear? That is the point that is being made. Okay. Now, let us look at the other instance. What happens when R is 0? when r is 0, x 1 becomes, what is x 1? R is 0, x 1 becomes 0, and therefore, this equation becomes that of a PFR, which we have talked about. So, you can see the consistency. When r is 0, it becomes same as what we have done already. When r is infinity, it becomes another limit of what we have already done. So, in both cases, it tells you that recycle is between plug flow recycle, plug flow reactor and a stirred tank. So, it tells you that recycle is a device which makes you achieve any property between plug flow and mixed flow. That is what it says. Okay. That our definition makes it possible to do this. So, let us plot this and see what it means. So, when you make a plot of 1 by R A versus x, see 1 by R A versus x means what? It is the property of a reaction. See 1 by R A comes from our experiment. So, this data comes from our experiment. So, this curve comes from our experiment. When recycle is small means what? X 1 is what? X 1 is R by R plus 1, correct. So, x 1 is, when r is small, then you have this large area. When r is large, there is very small area, you can see here. So, r is very large, it becomes a point, it becomes a point. So, you can see when you increase r, when r is 0, it becomes PFR, you can see here. When r is infinity, it becomes a point which is CSTR, you can see, understand. So, going from 0 to infinity, you are able to get various properties between mixed flow and plug flow. Now, let us just see quickly how does a first order, let us say you conduct a first order reaction in a recycled plug flow reactor, let us say. So, what is our design equation? So, this minus of R A, I have replaced it by a first order representation, which is k times C A 0 times 1 minus of x A, correct. So, x 1 is R by R plus 1, x 3 is correct. So, I have just integrated and put them down. Therefore, our plug flow recycle for a first order reaction with recycle ratio R, this is our integrated form of the design equation when it is a first order reaction. Beautiful question, but that answer I thought we have already done, but let me do it again. Now that you asked me, I want to do this again. I will do this here. So, your question is, what is CA? Basically, what is CA? CA is what? FA divided by volumetric flow. What is FA? R plus 1 FA 0 into 1 minus of x A, correct. What is V? Let us say it is a gas phase reaction, V by V 0 is F t by F t 0, T by T 0, Z by Z 0, P 0 by P, and we now showed just now all these, if it is 1, this is equal to R plus 1 into what did we show here? R plus 1 into 1 plus y a 0 x a time. We have shown just now, if you recall. That means, in the denominator you will have this term R plus 1 times 1 plus y a 0 x a times delta A. Okay. Now, I have taken the instance of A going to products, therefore, all these are not there, this cancels off, therefore, it becomes C A 0 times 1 minus of x A. V becomes V 0 times this, R plus 1 cancels off, this becomes 1, therefore, it becomes C A 0 times 1 minus of x A. Or in other words, inside the recycle loop, the concentration dependence of x does not change, because the formulation we have taken is like that. That is the importance of the formulation. That formulation, in this formulation, the form of the CA still remains the same. That is the advantage. If you take any other formulation, then it is a little bit messy. It is a little messy. So, it will still give you the same correct result only, but this formulation makes it very elegant. Okay? Is it okay? Shall we go forward? Yes. So, what are we saying? What we are saying is that, that if you have a recycled reactor, then the integrated representation for a first order reaction is given by this. Is that clear? Okay. So, which means what? If you are given a recycle ratio, see here what are the unknowns? K is unknown, R is unknown, X 3 is unknown, tau R is unknown. Now, out of 4, if you are given 3, you can calculate the 4th. That is the kind of, you can have a design problem, the operation problem, whatever problem, apparently appropriately you will have to put your numbers here to find out what the numbers that you are desiring. Now, in order to understand the importance of recycled reactor in a larger context, let us look at a small example. The example I have taken is an n tank sequence. So, what is an n tank sequence? You have stirred tanks 1 to n, in which I have taken a reaction which is first order. I have taken a first order reaction which is R A is taken as minus K times C A. A goes to products, therefore, there is no volume change, for which I have written the material balance input output generation equal to 0. Okay. Is that clear? So, I have put the generation term here. So, for C A 1 becomes C A 0 divided by 1 plus K tau 1. Okay. Similarly, C A 2 equal to C A 0 divided by this. Okay. Let us just take this analysis forward a little, because it is important. What we are saying is that C A n becomes C A 0 divided by K tau by n to the power of n. How does it come? It comes from here C A n, from here C A n becomes like this number of terms tau 1, tau 2, they are all considered equal to tau divided by n, that is the assumption. Therefore, you get this kind of representation. That means, the value of concentration at the end of the nth tank is C A 0 divided by this term. Okay. Now, we can do this manipulation, I have just elementary manipulation, I have just put this in this form, where K times tau n becomes n times 1 minus x to the power of x n to the power of 1 by n minus 1. It is a very elementary manipulation I have done, because C A 0 by C A n is 1 minus x to the power of n, it is common sense, correct. Therefore, what it gives you is that a n tank sequence, the conversion at the end of the nth tank is related to system parameters like this. Now, let me just put this in the context of our interest. What is our interest? Our interest is to understand the 3 types of equipment we have learned so far. We have learnt this is a PFR. Okay. We just now set up the equation for a recycle. We set up this as a recycled reactor. Now, just now we talked about an n tank sequence where we got this relationship, okay, which I have put down here. So, you have a case of PFR where there is no mixing. You have the case of a recycled reactor with R as the recycled ratio. Here the case of an n tank sequence where you have K tau n is the parameter, K tau r is the parameter here, K tau p is the parameter here. Now, what has changed from here to here? From here to here, what has changed is that it is a recycle, we have put in a recycle. What has changed from here to here? Instead of a no mixing case, it is infinite mixing case, is an instance of n tank, n tending to infinity is a huge amount of mixing. Or when the number of tanks is small, it is intermediate mixing. Okay. See, when you go to n equal to infinity, we have shown it is same as a PFR, we have shown that. When r equal to 0, we said it is same as a PFR. So, r equal to 0 is equivalent to n equal to infinity, okay. Or in both cases, r is a measure of mixing, n is a measure of mixing, because n is able to give you property between plug flow to mixed flow. When n is infinity, it is plug flow. When n is 0, it is a single stirred tank, infinite mixing. So, what it means is that when you go from a PFR to a recycled reactor to an n tank sequence, you are able to take into account various grades of mixing that can occur in your equipment, which is what happens in the real life. In real life, you have to deal with mixing. It may not be perfect, it may be imperfect. So, recycled reactor or value of R as a parameter and similarly n as a parameter is a way of accounting for non-idealities due to mixing in your equipment. So, to summarize this, let us just look at an example. Let us say you have an arbitrary vessel. What is this arbitrary vessel? We do not know what it is. So, we are doing an experiment in which you are putting Fa 0, you get a conversion of Xa. I ask you, now what is it a plug flow reactor? What is it? We do not know. What do we do now? We simply make a plot. Now, we can make a plot of this function. We can make a plot of this function. So, I have done this here. I make a plot of this function, recycled reactor function here, and I made a plot of the n tank sequence here. So, this is function relating n tank sequence, this is for a recycled reactor. As x versus r, as r increases, which means conversion decreases. As R increases, that means R is 0 is PFR, R infinity is CSTR, conversion will keep decreasing. N tank sequence x n infinity is a PFR. So, x will increase, is that clear? So, value of R and value of n are measures of mixing. Suppose you get a conversion of x a in your experiment. So, you will read out a value of R from here, you will read out a value of n from here. Okay. That means, this arbitrary vessel can be described by a value of R or by a value of n, and in both, in that case, if it is value of n, it will be described by this function, if it is value of R, it will be described by this function. So, which means, we have a way of describing real life problems. It is no longer idealized, it is a real life problem. Whatever be the arbitrary system that you have, you are able to relate it to some fundamental way of understanding reality. So, that is the advantage of these two equations. An arbitrary system can be understood in terms of recycle ratio, can be understood in terms of number of tanks. Of course, we should know the system parameters, which is k tau r and k tau n, which comes from independent measurements. So, having said this, let us see what is the kind of use to which we can put recycle reactor to. So, now if you look at recycle reactor, what it says is, recycle reactor feeds products into the process, correct. See, what does it do? It puts our products back into the process. Where is the advantage? The advantage is in reactions where you require to put products into the feed, otherwise reaction does not go forward. There are autocatalytic reactions, they are good examples. All biological reactions require products to be put into the feed, and therefore, it is very useful in biological reactions. Now, there is another important is it allows adjustments of velocities through the reactor. When you are doing an experiment in the or laboratory development, you can do your experiment at various velocities. Therefore, you can see how good is your catalyst to be able to stand the velocities of your industrial use. Therefore, you can appropriately design it for the kind of industrial operation that you are going to have, of which I mentioned a little earlier, is that see, it allows you to do a very low per pass conversion. When you have very large recycles, per pass conversion is quite low, which means essentially isothermal operation becomes possible, and therefore, you can do kinetic measurements in a recycle reactor. And therefore, you will find in catalyst development, for example, recycle reactors become particularly useful, because you are able to get very good catalytic measurements and essentially isothermal operation. It may be very highly exothermic reaction, but because of a very large recycle, per pass conversions are so low that you are able to get isothermal data. So, these are the three important advantages that you will have with recycle reactors. Okay. Having said this, the real applications that you will see, I mean we all have seen is that in autocatalytic reactions of recycle reactors. So, when you make a plot, so the reaction A goes to B, where the rate function looks like this. When you plot R A versus X or concentration, if it is plotted like this, the progress reaction looks like this. If you plot it like this, progress of reaction looks like this. The important point is autocatalytic reactions show a maxima in reaction rate. This is the most important thing, they show a maxima in reaction rate. Why do they show a maxima? Because as the products accumulate, you will find that the reaction goes up and then comes down. Okay. So, this feature of maxima in reaction rate or minima in this kind of plot is useful in design, because if you can design your system at this point, your reaction equipment volumes are very low, highest, because the reaction rates are very high. So, there is an advantage, but at the same time the disadvantage is that the conversions may not be high enough. You see various issues like this, which becomes important in design. Having said this, let us just look at this in some detail. This is 1 by R A versus X, 1 by R A versus X. Now, this is a recycled reactor, this is the point of maxima in reaction rate. Now, when you have a small recycle, large recycle. Okay. Small recycle, large recycle. Now, if I ask you what is the best value of recycle ratio you would employ? Okay. What is the best value of recycle ratio you would employ? Our answer would be, listen, if you look at this function R plus 1 increases as R increases. But this function here dx by minus of R A, what happens to this function? dx by minus of R A. This you can see this function here, you can see it decreases and then increases. So, or in other words, this is an increasing function, but it has a decreasing and increasing function. Therefore, there is an optima. There is an optima, that means recycled reactor employed in autocatalytic reactions, there is an optimum value of recycle ratio, which gives you the minimum volume. Okay. Now, if you ask what is that minimum volume, of course, we can set up this equation, put the appropriate functions here, you will be able to find out the minimum where it occurs. Okay. But there are mathematical techniques by which you can show, I have not shown it here, it is an exercise in your problem sheet, you can show this result. What result is that? Optimum recycle, that optimum exists, it come by looking at the shape of this curve, you can tell optimum exists. What is the optimum? You will be able to show, but we have not done it here, it is an exercise in that the optimum recycle puts into the reaction equipment, that means optimum recycle, the optimum recycle puts into position 1, this position 1 a feed, it puts a feed into position 1, which is actually satisfies this relationship. What is this relationship? The optimum recycle, that means the reaction rate at this point, which is 1 by R A at x 1. 1 by R A at x 1 is the average of this whole thing. What is this term? Dx by minus of R A x 1 to x 2 divided by x 2 minus of x 1. This is the average value of this rate over that interval. Is it clear? The right hand side, integral x 1 to x 2 dx by minus R A divided by x 2 minus of x 1 is the average value of this function in that interval x 2 to x 1. This is x 2 to x 1 is this, which means what? The optimum recycle puts into the reactor a feed whose 1 by R A at x 1, 1 by R A x 1 is the mean in the range x 1 to x 2. Okay. We will show this mathematically also, but since it takes a little while, I put it as an exercise. I have not shown it here, but we will do it as an exercise as we go along. But it is understood in physically, what is important to understand is optimum means what? You are choosing a value of R such that the reaction rate measured as 1 by R A at x 1 is the average that you would have gotten in the whole equipment. So, now that optimum recycle exists, and the optimum recycle either can be found mathematically or graphically as possible. Now, there are some interesting issues that happens in autocatalytic reactions, something that some of us may have appreciated, but I thought it is important to draw attention to this. See, when you write the design equation for a CSTR, in which an autocatalytic reaction is taking place, our design equation looks like this: V by F A 0 is equal to x by minus of R A. R A I have taken, our R A value is minus of k times C A C B. This is what I have substituted with a minus, therefore, it has become plus sign. Now, I have replaced C A and C B using our conventional stoichiometry. Now, if you look at this equation carefully, what it says is, if I specify a conversion x that I want, straight away you will be able to find the size of the equipment. Okay. Now, in the way it is formulated here, it does not say that the feed, this feed should contain C B 0. It says C B 0 can be 0, because this result tells us that it does not matter. C B 0 need not be present in the feed. Is that clear? What we are saying is that if you have an autocatalytic reaction being conducted in a CSTR, as per the design equation that we have written, C B 0 can be 0. That means, it is not necessary for you to put the product in the feed, even then the reaction would occur, and there is a finite value of x you will calculate, and for which the volume can be specified. Or in other words, it seems a little difficult to understand why is it that autocatalytic reaction, which should not take place if there is no product in the feed, our design equation seems to suggest the reaction will occur. Okay. So, there is appears to be some inconsistency in the way we have formulated our problem. So, we need to sort out this, or at least to understand why this kind of inconsistency, it appears to be inconsistent. So, we want to understand this. How do we understand this? To understand this, what I have done is, I have written the unsteady state equations. So, what happens in the unsteady state? Once we understand the unsteady state, we can understand the steady state. After all, what is steady state? after a very long time of the unsteady state, the steady state is attained. So, what is this equation? It says input output generation equal to accumulation, correct. So, for component A, component B, I have written for component A, this for component A, this for component B. Okay. This for component A and this for component B. Look carefully at the two equations. Okay. So, I am saying a T equal to 0, Ca equal to Cai, Cb equal to Cbi. Let us look at the situations when Cbi is 0. Okay, what happens? When Cbi is finite, what happens? What is Cbi and Cai? Cbi and Cai is what is in this equipment when we started this reactor some a million years ago, as an example, long time back. But today we are running it with Ca 0 equal to some value, but Cb 0 is 0. But when we started this reactor some time back in the past, there was Cbi, there was Cai, we do not know what it was. Let us see what might have happened during the startup. Let us say case 1, Cai is 0, so and Cbi is not 0. Ci is 0, but Cbi is not 0. Now, what happens to this function? Ca at time t equal to 0, Ca is 0, therefore, reaction rate is 0. Okay. But Ca is coming in, therefore, after some time Ca would become non-zero. That means, if Cbi was finite, the reaction would started to take place once Ca starts coming into the process. As per equation 1, you can see here input, output, generation, accumulation. When you started the reactor, Cbi is finite, Ca is 0, but Cbi is not 0. Therefore, this term, it was 0 when you at 0 time, but a little while later Ca has started coming in, therefore, there is Ca in the reactor, therefore, this term is finite. Therefore, this reaction would go, this reaction would take place. Is that clear what we are saying? This reaction would take place because after at time t 0 plus, this term is finite, and therefore, this reaction would take place. Therefore, this equation can be integrated, this equation also can be integrated, and therefore, it will tell you how long it will take to reach steady state. See here, what we are saying is that continuous input of Cb is 0. See what happens, please, it is an important question, please, it is a very important question, let me answer this question. See, whenever we have an equipment, we would start up that equipment sometime in the past. After all, we have to start the process someday at the past. At the day when you first started that process, if you had put Cbi into your tank, what it says is that Cbi would be active, however small it may be, so that this Ca times Cb becomes finite after time 0 plus. Therefore, this reaction takes off. Therefore, this reaction takes off. Therefore, these two equations 1 and 2 can be integrated, and it will tell you how long it will take to reach steady state. At that steady state, it may not recognize Cai and Cbi, it will get steady state values as described by our steady state equations. Where are we? These are the steady state equations. So, the steady state equations will describe our steady state problem, but this equation here will tell you how long you would have taken to reach steady state. Or in other words, what we are saying is that if you have an autocatalytic reaction, as long as you have Cbi is non-zero when you start the process sometime in the history of that, it is enough as far as the reactor to reach a steady state value in which your products are positive.
So, the reaction will start only when something like Ca will
Cb.
So, Cbi is not 0, but
Ca is there na, Ca is coming na.
Ca is coming.
Yes.
When a little Ca not is come, then
reaction will take place. Reaction will take place. That is what it says. All it says is the time that is required to reach steady state will be determined by the value of Cbi and Cai.
But it tells us that the Cbi should be there initially.
Yes, during the history. During the history.
So, if a new reactor is there,
So, that means the day we start up the new reactor, you have to put some Cbi, but you do not have to put it every day. Once the reactor has started, it has to be, it is not required. But having said this, I want to remind you, see, after all, we do not want to wait for a very long time to reach steady state. After all, a process has to run, it has to reach steady state quickly. So, for that to happen, you may add Cbi every day. So, that is a decision that you will take, but what our formulation tells you is that our steady state will not depend upon the quantity of CBI and CAI. Steady state is independent of the choice of the initial state. Is that clear? So, what we are trying to point out here is that I have to stop here, that steady states that you will reach for autocatalytic reactions, you do not require CBI and CAI in the process. It is not required. It is required only during startup. I will stop there.